Equivariant graph neural networks have been explored for learning more accurate dynamic interaction models in particle-based fluid mechanics. Two well-known fluid flow systems, the 3D decaying Taylor-Green vortex and the 3D reverse Poiseuille flow, were benchmarked to compare the performance of equivariant graph neural networks against their non-equivariant counterparts. Navier-Stokes equations are ubiquitous in fluid mechanics, hydrodynamics, and weather modeling. However, these equations are often analytically intractable, necessitating numerical solution schemes. These schemes can be categorized into grid, mesh-based methods, also known as Eulerian description, and particle-based methods, or Lagrangian description. One such particle-based method is smooth particle hydrodynamics, or SPH, which was independently developed by Gingold and Monahan and Lucy in 1977 to simulate astrophysical systems. Since its inception, SPH has become a preferred method in various applications, including free surfaces like ocean waves, fluid structure interaction systems, and selective laser melting in additive manufacturing. The main contribution of this work is the application of equivariant graph neural networks to learn more accurate dynamic interaction models in particle-based fluid mechanics. The authors compared the performance of these networks to their non-equivariant counterparts on different performance measures, such as kinetic energy and Sinkhorn distance, which are typically used in engineering to validate numerical solvers. The results indicate that equivariant models learn more physically accurate interactions, albeit at the cost of slower training and evaluation times. This suggests opportunities for future work towards coarse-grained models for turbulent flows and generalization across system dynamics and parameters. A novel machine learning model, the Graph Network-Based Simulator (GNS) framework, is implemented for fluid mechanics simulations, with a focus on the Taylor-Green vortex and reverse Poiseuille flow as test cases. The GNS model employs an encoder-processor-decoder architecture with message-passing layers to predict the next state of a particle system in a Lagrangian fluid mechanics simulation. This framework is built upon simple multi-layer perceptrons, MLPs, and has shown promising results in engineering particle-based simulations. The dataset consists of 8,000 training, 2,000 validation, and 2,000 testing instances for both the Taylor-Green vortex and reverse Poiseuille flow. Each instance represents the state of a particle system at a given time, comprising n particles, where each particle's state vector includes its current position and a time sequence of previous velocity vectors. An interaction radius of 1.5 times the average interparticle distance is employed to construct the connectivity graph, resulting in approximately 1021 hop neighbors for each node. This approach enables the GNS model to learn the dynamics of fluid flow from discrete particle interactions and predict future states based on these interactions. The primary goal of this research is to demonstrate the applicability of learned approaches to reproducing numerical solver results for fluid mechanics simulations. By leveraging the GNS framework, the authors aim to show that such models can be effective in predicting fluid flow behavior over large time steps, potentially surpassing traditional numerical solvers in terms of efficiency and accuracy. The steerable E3 equivariant graph neural network, SEGNN, is a machine learning model designed to predict fluid dynamics. It's an instance of E3 equivariant GNNs, which are tailored towards molecular property prediction tasks and incorporate general steerable node and edge attributes. These attributes can represent any physical quantity, directly learning the weights of the Klebsch-Gordon tensor product. The choice of edge and node attributes significantly impacts the Klebsch-Gordon tensor products, making it crucial to find physically meaningful attributes for good performance. In this implementation, edge attributes are chosen as spherical harmonic embeddings of pairwise distances, while node attributes are a combination of averaged historical velocities and the sum of edge attributes from neighboring particles. Training involves adding Gaussian noise to the inputs and explicitly concatenating the external force vector to the node features, improving performance, especially in the reverse Poiseuille flow case. The SEGNN model is compared to a Gaussian neural spline (GNS) model, a non-equivariant baseline, on two fluid flow datasets, Taylor-Green vortex and reverse Poiseuille flow. Both models have similar numbers of parameters for the Taylor-Green dataset, but SEGNN has fewer parameters for the reverse Poiseuille flow. Although SEGNN models are slower due to the constraints of the Klebsch-Gordon tensor product implementation, they outperform GNS in terms of mean squared error of particle positions, Sinkhorn distance, and kinetic energy, particularly in the Taylor-Green vortex experiment. The Taylor-Green vortex experiment poses a challenge due to varying input and output scales throughout a trajectory, leading to the importance of first-time steps in the loss. Both models generally match the ground truth kinetic energy well, but GNS drifts away from the reference SPH curve earlier. The rollout mean squared error for this case matches the behavior seen in kinetic energy. The paper explores the application of equivariant models in capturing underlying physics properties of particle-based fluid mechanics systems. It presents a comparative analysis between the SEGNN and GNS models, with SEGNN demonstrating superior performance in terms of mean squared error, MSE, for pressure and kinetic energy, Sinkhorn distance, and inference time. The SEGNN model shows better reproduction of particle distribution and smaller deviation from the ground truth, particularly in the Taylor-Green vortex and reverse Poiseuille flow problems. The study also highlights potential avenues for future research, including enforcing physical behaviors such as homogeneous particle distributions and incorporating recent developments for neural PDE training. Combining these strategies with equivariant models could lead to promising solutions for long-standing problems in fluid mechanics, like learning coarse-grained representations of turbulent flow problems or multi-resolution dynamics of Navier-Stokes equations. Physics-informed neural networks have emerged as a powerful tool in solving complex physics problems, leveraging deep learning frameworks to tackle forward and inverse problems involving nonlinear partial differential equations. This concept was first introduced by Récy et al., who demonstrated the potential of these networks in enhancing our understanding of various physical phenomena. In addition to this, the importance of geometric and physical quantities in enhancing the performance of E3 equivariant message passing has been highlighted by Brandstetter et al. Their work emphasizes the significance of incorporating domain-specific knowledge into neural network architectures, leading to improved accuracy and efficiency in solving physics-based problems. Graph networks have also been proposed as a means of learning to simulate complex physics, as demonstrated by Sanchez-Gonzalez et al. These networks can effectively model complex systems and their interactions, providing insights into various physical processes and phenomena. Another key concept discussed in the paper is smooth particle hydrodynamics, which has been applied in different contexts such as astrophysics and fluid dynamics. For instance, Gingold and Monahan developed a method for non-spherical stars, while Hu et al. Proposed a consistent multi-resolution smooth particle hydrodynamics method. These advancements have significantly contributed to our understanding of complex fluid behaviors and their applications in various fields. Furthermore, the paper mentions the work of Li et al., who introduced the Fourier neural operator for parametric partial differential equations. This method utilizes a deep learning framework to solve a wide range of PDEs, making it a powerful tool for various fields of physics and engineering. The Fourier neural operator has shown promising results in solving complex problems that are difficult or impossible to solve analytically, paving the way for further research and development in this area. In conclusion, the paper provides an overview of various aspects of physics-informed neural networks and their applications in solving complex physics problems. By leveraging deep learning frameworks and incorporating domain-specific knowledge, these networks have the potential to revolutionize our understanding of various physical phenomena and processes. The appendix presents reverse Poiseuille plots, a critical component in evaluating the performance of the proposed smooth particle hydrodynamics (SPH) model. Figure 3 displays the reverse Poiseuille XY view of velocity fields and position error at time steps 10, 500, 990, from left to right of the test rollout. This visualization tool is used to assess the accuracy of SPH simulations, particularly in capturing complex fluid flow behavior. By examining velocity fields and position error at various time steps, researchers can gain insights into the model's ability to reproduce real-world phenomena. The authors draw inspiration from previous works on SPH, citing contributions such as Jeffrey Ingram Taylor and Albert Edward Green's 1937 work on the mechanism of small eddy production, Damien Violo and Benedict D. Rogers, 2016, Overview of the Past, Present, and Future of SPH for Free Surface Flows, Johannes Weirather et al., 2019, SPH Modeling for Laser Beam Melting, and Kai Zhang et al., 2021, Multi-Resolution SPH Method for Fluid Structure Interactions. These references underscore the significance of SPH in simulating various fluid dynamics scenarios.